Okay, so let's resume our discussion on renormalization group equations. And till now we have seen how the coupling constant changes as you change the renormalization scale mu. Okay, that's something we saw earlier. And we had defined beta tilde, which is a function of lambda r, okay, and epsilon only in when you are away from 4 dimensions. So we took d equal to 4 minus 2 epsilon. Okay, and in MS bar scheme it depends only on lambda r and epsilon. In general scheme it will depend also on mr, okay, and mu also explicitly. But in this case the mu dependence is implicit in this scheme, and this was defined to be d lambda r over d mu. Okay, let's see what else we had done earlier. Yeah, and also we saw that the contribution to beta tilde or the beta function comes from only the single pole terms. Okay, so let's see what this A1 is. A1 is here. So this Z lambda, which is the renormalization constant for the coupling constant, here I have written not in terms of, not as an expansion in lambda r, but rather I have collected terms according to the order of poles. So A1 has all the terms which give you a single pole. Okay, so this A1 gets contributions from all orders in perturbation theory. Okay, so when you do a two-loop calculation, you also generate double pole and a single pole. So that is also included in here. So there are lambda r terms, lambda r square terms, lambda r cube terms, and so forth. Same for this. And we saw that because of this relation, the beta function gets contributions only from the single pole terms. Okay, and the higher order pole terms, their coefficients do not contribute. Okay. Now I want to look at how the mass parameter should be changed when you change the scale mu. Okay, and I should remind again that mu is not a physical parameter in your theory, because you see that is not something present in the bare Lagrangian. So that cannot be a parameter of your theory, and it cannot be related to any of the physical scales in the theory or physical scales in some experiment. Okay, if you are doing some scattering, mu cannot be related to any of the scales in the scattering experiment. Okay, the incoming momenta, outgoing momenta, whatever. Okay, because that's simply not present. And what we are trying to learn here is that if we were to change mu, how I should change the coupling constants, the renormalized coupling constants, such that the theory remains unchanged. Okay, meaning such the change should be such that in the renormalized couplings and the renormalized mass parameters, such that the bare parameters do not change. Okay, so now before I move on to look at how the renormalized mass should change with the scale mu, I want to make a correction. There is a mistake I have done earlier, which is giving a wrong result for the beta function by a factor of 2. I'll just tell you what that mistake is. Okay, so let's go to this other notebook. So I should go to where I was doing renormalization of 5-4 theory. Yes, here. Okay. So now here you see this vertex is of order lambda r square, okay? Because when you have done written the action in terms of renormalized fields and parameters, this is a term which you produce, okay? That has an explicit lambda r here, and because of the z's, you get another factor of lambda r. I mean, it starts at order lambda r, this piece, so that's why it's lambda r square. So we have this vertex. Now we started calculating these 2-point function and 4-point function and renormalizing them. And somewhere here it went wrong. Yeah. Here. I hope I'm not losing. Yes. So you see, I'm looking at this renormalization of 4-point function. Okay. Here. So I calculated all these 3 diagrams at one loop, and these had some poles here which we wanted to cancel, and that for that I need to adjust the z that appears in here in this vertex. Okay. So I wrote the expression of this 4-point function where I'm using the counter term, and you see, after writing all these factors, after counting all this, I multiplied by 1 over 2 factorial. Okay, and the reason why I multiplied by this 1 2 factorial was the following. So if you recall how our Green's functions are written, I'm just writing the numerator part. We had learned this in the first course. So you have, okay, I'm just writing Green's functions in the coordinate space. Okay, here in this case it will be 4, but I'm just writing generic 1. Tau. Okay, this is what you get in the numerator, and it is basically this which you are expanding here and writing. This is what gave you the Feynman diagrams. So now here you see our H interaction or HI is contains this term which you had in the action. Where is that? Okay, it is way behind. Yeah, here. Okay, so HI will contain all these terms starting from here to this last one. Okay, because these all are having coupling constants in them. Okay, so that is what enters. Now the mistake that I made, it was a slip of mind, was the following. Where did that go? Sorry, lost track. Yeah, here. So when I put HI, okay, here, that all those terms which I was telling, when they are here, and I expand. So when I expand the exponential, the first term is 1. Okay, then the next term will be this exactly this thing in the argument. Okay. Then the next one will be the square of this times 1 over 2 factorial. Then the third term would be cube of this times 1 over 3 factorial. And this is that 1 over 2 factorial and 1 over 3 factorial, that is what comes here usually. Okay, that is what I was saying. But note that when I expand to the first order, it will be 1 over 1 factorial, not 2 factorial, 1 over 1 factorial times this piece. But this piece includes this this vertex, which is already order lambda r square. Okay, So even though I have a term which is order lambda r square, okay, you do not get that 1 over 2 factorial. Okay, this would have been true if none of the terms in hi would be lambda r square. If they were all linear in lambda r, then only when you go to the next order term, you get lambda r square and you bring 1 over 2 factorial. Okay, so that's the mistake. I should not have included this one. So this should go away. Okay, if this goes away, then this should go away. And then z lambda should become 3 over 32 pi square. Okay, so let me try to make that change. Sorry. So this should become 32 pi square. Why doesn't it go away? Okay. So this is a correction that I wanted to make. Now let's return to our discussion on how MR changes with mu in 5-4 theory. Or the discussion will be general, but let's see. Okay, so back to business. So our question is, did I give an expression for this one? No. So you should exercise. You should check that you get beta tilde lambda r epsilon in 5-4 theory to be minus 2 epsilon lambda r. This is this term plus 2. Maybe I'll just give you the answer. Plus 3 over 16 pi square lambda r square. Okay, so all you have to do is take the derivative of a1, and that derivative of a1 you can find from the z of lambda that I have just corrected. Okay, so that's the beta function in 5-4 theory. Let's go to the question of how MR changes with mu. Okay, and you already know why we are doing this. Okay, so as before, we want to keep the bare mass parameter fixed as I change mu, meaning this derivative should be 0. And again, it's customary to put a mu here. Okay, which is same as writing mu d over d mu Zm times Mr. That's hopeless. And this should be equal to 0. Okay. Okay, so we take this derivative and should be 0, which is just which gives you mu after taking the derivative, I am going to divide by Zm and Mr. Okay, so that gives you mu over Zm dzm over d mu plus mu over Mr dmr over d mu equal to 0. Okay. Now I will define gamma m as minus mu over Mr dmr over d mu. See, this gamma m is dimensionless because Mr has mass dimension 1, mu has mass dimension 1. So this ratio is dimensionless and this ratio is also dimensionless, and that's why I have divided by Mr, unlike the case in the beta function, so as to make this gamma m dimensionless. Okay, so gamma m is dimensionless. Okay, and this gives us gamma m. So I will use this equation, and this gives us gamma m is mu 1 over Zm dzm over d mu. Okay. Now again, repeating very similar steps as we did for the beta function. Let's so I'll take this equation, which is derivative with respect to mu, but I know that Zm, this renormalization constants in the perturbation theory in MS scheme, they do not depend on mu explicitly, they depend only on lambda r. So let me, instead of using total derivative with respect to mu, convert it to a derivative with respect to lambda r. Okay, that's what I'll do now. So you, as before, you get mu d over d mu is equal to mu del over del mu plus del over del lambda r, and then del lambda r over del d lambda r over d mu times mu, that is beta function. Okay, that is beta tilde. Or maybe I can write it closer. Plus del over del mr mu times dmr over d mu. Okay, and these will give you 0. Okay, when you act this thing on Zm, because again, for the same reason, no explicit dependence on mu, no explicit dependence on Mr when you are working in MS bar scheme or MS scheme. Okay, so what do we get? We get gamma m. So here I am now substituting that. So mu d z over d mu I will replace by beta tilde times del over del lambda r, and then I get gamma m is beta tilde over Zm del Zm over del lambda r. Okay, so now I can take the derivative easily because everything is in the Z, everything is with respect it's just a function of lambda r and epsilon, so I can take a derivative with lambda r. You can replace this by a total derivative because Zm depends only on lambda r, right? There is no other variable. Okay, so now let's again do what we did earlier. So I'll write gamma m times Zm is equal to beta tilde times, remember Zm we had written as, okay, this is again not writing this, horrible, 1 plus b1 over epsilon plus b2 over epsilon square and so forth. Okay, I had collected all the single pole terms, double pole terms and etc. So this I will write as, when I take the derivative, that one goes away and it gives you dv1 over d lambda r times 1 over epsilon, okay, plus dB2 over d lambda r times 1 over epsilon square, and other terms. Okay. Now we should put expression of beta tilde and Zm here. Okay. And exactly as before, you compare order by order, you compare the powers of epsilon to the n on both sides. So here you write Zm as like this. Okay. So, and here you put the expression of beta tilde, which is already I wrote just now a little while ago. Here, this expression. Okay, you substitute it there, and then you can compare order by order, and you will see that the expression for gamma m is minus 2 lambda r dB1 over d lambda r. Okay, that's what you get. And now you see that the gamma m, okay, gamma m is the thing which controls how mr is going to change as you change mu, right? That's what controls the behavior of mr with mu. Okay, that's the derivative of mr, and derivative of mr is controlled by gamma m. Okay, and now we have seen that gamma m depends only on B1. It does not depend on B2 or B3, meaning it is controlled by the coefficients of single pole terms only. Okay, very naively one would think that all the coefficients, whether it is coming from single pole or double pole or triple pole, they will contribute. So for example, at 2 loop you have both double pole and single pole. At 3 loop you will have triple pole, meaning pole of degree 3 and degree 2 and degree 1. So naively one would think that they all should contribute, but we see here explicitly that only B1 contributes. Okay, only the coefficients of single poles contribute. So now we can, that's a generic result. Okay, it has, we have not used the fact that we are using 5-4 theory. Okay, this is true for any theory. Now I will write results specifically for 5-4 theory. And of course you can do similarly for whatever theory you are interested in. So for 5-4 theory, oops. So for 5 to the 4 theory, okay, we have already seen that Zm is 1 plus 1 over 32 pi square 1 over epsilon lambda r plus order lambda r square terms. Okay, so right now I am going to give an expression which is true only up to order lambda r. Okay, because other single pole terms from order lambda r square order lambda r cube I have not calculated, so I don't have them here. So I will be using only this one. Okay, so Zm is this. So what is B1? B1 is this part, 1 over 32 pi square times lambda r. Okay, so gamma m is minus 2 times lambda r, okay, times this factor, which makes it minus 1 over 16 pi square lambda r. Okay, so we have also an explicit result for gamma m in this 5-4 theory. Okay, now let me make some remarks about the beta function. So here we had mu d lambda r over d mu as beta tilde. Okay, and remember that we are doing perturbation theory. So suppose that in a theory, whichever theory you are looking at, this beta function turns out to be positive, meaning the rate of change of lambda with mu is positive. Okay, so as you increase mu, because beta tilde is positive, lambda r will increase. Okay, so if beta tilde is positive, then lambda r mu increases as you increase mu. Okay, and if beta tilde is negative, then this decreases as you increase mu. Okay, and that is a very useful piece of information, because that can you'll see why it's important. And actually in a particular theory, in particular set of theories, you get beta tilde to be negative, and Nobel Prize was also awarded for showing that beta function is negative in those theories. So anyhow, one of the important reasons why one is interested in the sign of beta function is precisely why these coupling constant, how these coupling constants behave as you change the scale of, as you change the scale mu. And actually we'll see later in detail why this beta function would be, why the sign of beta function would be interesting for us. Okay, when we analyze more in more detail about the renormalization group equations. Okay, when we analyze how Green's functions behave as you change scales, and how they behave when you scale up the physical momenta. Okay, right now I'm talking only about the mu, which is non-physical. It's not a parameter really in your theory. Things should be independent of mu. Okay, but later I will relate things, the behavior of Green's functions, to the change of scale of physical momenta in the theory. Okay, and I will be interested in high energy behavior. So anyway, we'll see all that in the next video, or we'll start going towards that in the next video. And I hope you have an understanding of what these beta functions and what this gamma m are doing, and how they can be calculated in perturbation theory. Also, one remark, that suppose you calculate beta function and it turns out to be positive. Okay, like here in this case it is positive, so beta 1 is positive. So as you increase the scale mu, this lambda starts growing. Okay, but then that will not that expression you cannot use after a while, because once the lambda r has become large, sufficiently large, okay, or of the order 1, then you cannot use the perturbation theory anymore, because having a perturbation theory means that the parameter with which you are doing perturbation theory is small. Okay, meaning it makes sense to drop terms of higher orders in perturbation theory, and that you do because lambda r would be small, or the parameter perturbation parameter would be small. Okay, but as we see, if you are changing mu and it is increasing, then beyond a certain point lambda r would not be small anymore. So any conclusions that you draw from there when lambda r is not really small would not be really true. Okay, and you will need non-perturbative analysis for making any statements. But as long as you are in small lambda r region, okay, you can use such relations and conclude whatever you wish to, like whether lambda r is increasing with mu or not. Okay, so one has to be careful in not stretching perturbative arguments where they are not applicable. Okay, especially when couplings start becoming of the order 1. Okay, we'll meet in the next video and see what we do next.